Almost, huh? No. Okay. Welcome. Good afternoon. Welcome to 240. So, first, are there any questions? Yes. Sure.
We're using the break the loop strategy to find your T of S for the feedback. And in 140, a lot of times we would find your A and find your F, and then do the loading effects instead of doing the break the loop. Do you ever use that, or is that sort of not that useful?
Okay. Good point. So many of you took 140. What actually, if I may ask, what was the textbook? Okay, Meyer, a 4th edition, right? The green one. Yeah, if you actually looked at the book, and then it shows you 2 ways on how to analyze circuits. One of them is the 2-port approach, which apparently you use, and the other one is the return ratio approach. In the 2-port, I mean, both are valid as approaches. In the 2-port approach, as you said, you typically break things up into an amplifier that, I mean, I think it really, the approach really comes by and large from operational amplifiers. Right? You have a circuit like this one. There may be an operational amplifier in here or something, a transistor circuit, something like that, right? And you break it up into this port and this port, and you call this F of S and this A of S, right? And this one you somehow also need to include into the feedback circuit. Okay, and that would be shunt-shunt feedback. Now, when doing that analysis, you mentioned one problem. That is that you have to sort of simulate the loading effects, because the minute you take away this network from the feedback circuit, then of course the amplifier sees different loading, and it may behave different. Now again, if it's sort of sync operational amplifiers, then that's probably not too big a deal, because the output impedance here is very low, probably low compared to the loading from the feedback network. It kind of doesn't matter. There is another thing that is, but now the minute you use a transconductor here, then the story is different, right? The loading really matters, and then you kind of try to simulate the loading by hanging, for example, these 2 resistors in series here at the output to sort of simulate what their effect would be. And here you probably should, and rarely do, but you probably should add the input capacitance of the amplifier at that node, because that could give you extra phase shift, and of course we lower the phase margin of T of S, right? And if you did this in order to analyze stability, and we said that that's the reason, the number 1 reason why you do this exercise, well, then that wasn't such a good simplification. There is another reason why. So I mean, that says kind of, well, if you're dealing with op-amps, that's a very good thing. If you have transconductors, it's sort of less a good thing. And there is a third argument why I feel that why I find that this is no longer that practical, and that is that most of the time we use capacitors and not resistors in the feedback network. Well, in that 2-port analysis, for no fundamental reasons, but in practice, I mean, for example, the way it is written up in Gray and Meyer, the feedback network is always modeled as a unilateral circuit, meaning that current only flows in the direction from the output back to the input of the loop, right? With resistive feedback, that's usually a good idea because this node here has large swing, this node here has little swing, and so the current flowing forward here is kind of negligible, right? But when you have a capacitor here, that is no longer so. When you have a capacitor here, then at high frequency, very substantial current flows forward. And in particular with MOS transconductors, the current flowing forward through this capacitor here is actually more gets more significant than the current coming out of the transconductor. You know that because also in 140 you study this problem of the zero and this nulling resistor in phase compensation, all of that stuff. That's the reason, right? But your feedback analysis scheme that you used there didn't even tell you about it, right? In fact, what I always laugh about in Gray-Meyer is that there is this big chapter about feedback, and then finally comes a practical feedback circuit, right? Miller feedback, Miller compensation. And the feedback analysis schemes are not even used to analyze that circuit, right? So you can use the two-port thing, but be very careful. If you use transconductors, you really have to carefully account for the loading, and you have to include the feed-forward current through the capacitor also. Now, all of that said, a lot of equations have been developed to analyze feedback circuit, and lots of methods like the two-port stuff, the return ratio analysis that also is in Gray-Meyer. I invite you to read that. I find that a little bit more practical, actually. And typically I use that rather than the two-port solution. But anyways, sometimes over all of that we forget that the real reason why we need to cover feedback as a special case is that we need to be aware to check for T of S. T of S is nothing that we are fundamentally interested in, right? What we want to know is the closed-loop gain of the circuit. Well, looking at the closed-loop gain of a feedback circuit doesn't tell you anything about its stability, right? In fact, you can have you can run AC analysis of circuits in SPICE, circuits that are totally unstable, but the AC analysis just kind of looks fine, right? Sometimes it doesn't converge during trying to find the operating point, right? But if you really want to verify stability, then we have to look at T of S, and the other approach with SPICE also that kind of works is, and is a little bit more general even in some sense and more restricted in others, is transient analysis, because there we really can exercise the circuit in pretty much the same ways the real circuit would be exercised on the chip. So of all of that stuff there on feedback that you learned in 140, I think the main thing that you need to grab out is finding somehow the loop gain. And then you know, I mean, of course, yeah. Of course, I also do that, right? If I look at the circuit like this one, I say, oh, yeah, this is my feedback network. I calculate the ratio of these resistors, and I find the gain. Right? Then I implicitly kind of do two-port analysis. So, well, now you have my opinion. So I'm not going to teach return ratio analysis here. In a way, actually, I did the previous. I already threw it away, but what we went over last time, where we broke the loop at the ideal source, that is return ratio analysis. I mean, people call it that way. Big deal. I mean, it's normal nodal analysis. You just cut the loop at the particular point. There are also other strange things, like I found papers on. Not too surprising, if you make an approximation using two ports, you of course get a T of S, a loop gain that is hopefully very close to the real thing. Sometimes maybe it is the real thing, but usually we'll make a little bit of an error. Heck, it was an approximation, totally normal. If you do a return ratio analysis, you may make different assumptions, no assumptions, so you get a different T of S. Well, I've seen papers that compare then these two and sort of puzzle over their difference and say that the return ratio and the loop gain they are two different things. Well, that's a very bizarre thing to say. I mean, there is only one loop gain around the loop, and it determines the stability of the circuit, and that's the loop gain we want. If we use an approximation, we may have good reasons why we use that approximation, but then we get an approximation to that real thing, and there is only one real thing. So there is also not, I mean, for example, the Gray and Meyer text, it calls one thing return ratio, the other one it calls loop gain. Well, they really are the same thing. I mean, at least they are approximations of the same thing. If approximations. Other questions? So you see, even in this hot room, some things get me completely worked up. Okay, so the other one that kind of got me worked up was this thing. So now, I mean, the two-port thing, again, of course, is kind of nice because you would probably analyze this separately and the feedback network perhaps by hand even, this one with SPICE and this one by hand and so on. It kind of looks like you can verify the stability of this with SPICE. So a little bit simpler thing would be to use these tricks that are shown here that kind of keep the biasing and whatnot. But I think I've said enough about this that I probably disgusted you with this circuit. I also do not like it, and so let's turn the page. So now it becomes a little bit more sort of schematic, but in reality it's really the same thing. Here kind of we are breaking up the circuit also into two ports, but not into the amplifier and the feedback network, but kind of the amplifier, well, and the sort of the feedback port. Anyways, we are separating the circuit into two ports, and there is a connection between them that, when we break it, opens the feedback loop. This arrangement works for every circuit that has only one single feedback loop. We will get back to that point, whether that's a practical constraint or not. Anyways, we are now looking at how can we verify the loop gain and consequently stability using such a circuit. Now, if we have if we manage to sort of squeeze our circuit into this form, and my argument is that you always can do that, even if you're a multi-stage amplifier, then you can sort of lump all the gain terms of that multi-stage amplifier into this GM or AV or whatever it happens to be, right? Or X, and you can lump the load impedances all somehow together. I mean, there may be some work to do that, granted, but we've used this here only for a model to ultimately get. And then there was some other port some other impedance that drives the voltage that is the input to the amplifier port of this thing. So any circuit can be, if it has only one feedback loop or exactly one feedback loop, can be brought into this form. That's sort of believed. But then, of course, now we can calculate for this circuit here using completely normal nodal analysis. We can, for example, by breaking the feedback loop here and so on, using the return ratio trick that we looked at last time, we can figure out what is T of S, right? Okay. And T of S at that point depends on that gain and it depends on these impedances. So if we had some kind of a way to figure out what the gain and these impedances are, we could also figure out what is T of S. Right? So what we want now, I mean, of course, figure out what these impedances are with paper and pencil is tedious but possible. But what we really want is a way to do this with SPICE. And again, if we did it with paper and pencil, we would break the loop here. It would be pretty simple. But in SPICE, we cannot do that. Now there is a trick. And that trick goes back to a guy named Middlebrook. And he published his trick in '74. And the whole concept goes back even further to Bode, who in the 40s published actually this return ratio analysis. Anyways, point is that we take our circuit and we drive it first with a test signal. That's a voltage source. This voltage source will have DC-wise 0 volts. So it's just a short. I mean, we certainly haven't changed our circuit at all by inserting this voltage source. But now we run an AC analysis, and we look at the voltage that appears here and the voltage that appears here. Basically, the voltage that appears on the two terminals of this voltage source to ground. Right? We figure those out. And then again, it's a little bit of math to show that this voltage ratio is related to GM and these impedances. Okay? Fine. I mean, now we haven't really gained anything so far. We call that ratio TV, though. If you can use a little bit more zoom, then I just move my slide around. Okay, thanks. Okay, so that's the first thing that we've done. Then we do a second analysis. Here now we put the current source into a circuit, and again that current source, the DC current here is absolutely zero, and consequently it's like an open circuit. It doesn't change our device at all, right? And then we again get another ratio, and that ratio also is a function of the impedances that we are interested in. So now we have two equations, and we can now solve for the loop. Now we can calculate what the true loop. I mean, from before we know that the true loop gain is this thing, and now we can solve these three equations with three unknowns: GM, C1, and C2, and solve for T. Right? Okay, and the result is shown here. So that's kind of a bizarre equation, but if you type it into a computer, then who cares that it's bizarre, right? Right? Notice also that TV and TI are unitless, and T, of course, also is unitless. The loop gain is always unitless. The gain of an amplifier or the input-output, closed loop, open loop, or anything like that, right? Those gains, they're not necessarily unitless, but the loop gain better be unitless, because if we break the loop at some point, out comes a voltage, we stick in a voltage on the other side again, or likewise for current. Okay, so in practice, that's what we're going to do when we analyze the stability of a circuit with SPICE. We're going to run two analyses, and then using this equation, we combine the results of these two analyses and we plot T of S, a body plot of T of S, and then we use something like phase margin as our stability criteria. In practice, doing that, of course, is quite a bit of work with SPICE, right? One thing that I found to be quite convenient is I put my entire circuit into my entire amplifier with feedback and everything. Don't open anything into a sub-circuit, and I find a point somewhere where I can break all feedback loops. Those two I open there, and those two terminals I bring to the outside, and then I just run two analyses. One of them, this one here, where I put the voltage source across that breakpoint, and then I run a second analysis where I put the current source in. And you actually can run all of that in one single SPICE stack. You don't need to run run SPICE twice. And for that, you typically will use the alter statement. Who has ever used the alter statement? Okay, two or three, right? Okay, so now you all have an opportunity to familiarize yourselves with the alter statement. The alter statement just gives you an opportunity to sort of go to a certain point in the SPICE stack, run certain analysis and so on. Then you change your circuit using these alter statements. Right? Basically, you rip out this one, you stick in this one, in this case, and then you run another analysis. By doing so, you get all the right things, TV and TI, in one fell swoop, and then all you need to do is in the post-process, you have to type in this equation, do a body plot. You're done. Then it's not that terrible. Some more recent versions of SPICE, in particular Spectre, they have introduced a special analysis type that deals with that. So that's another option. To use a simulator can do it, and probably within 5 years or so, they probably all have it. Now, if you read the literature, and there are some citations later on in this lecture. Now a little bit different, less zoom. Thank you. then you may come across cases which explain that calculating a loop gain this way is numerically inaccurate, and they are correct in that for very small values of t, the accuracy of the simulation is not very good. So particularly if you have t of s 1 over 100, and you have set your reltol to 0.1%, the actual accuracy that you're getting out of your simulation is 100 times worse, or 10%. Well, 10% isn't a particularly good accuracy for your simulation. But you have two things that go for you there. One, well, probably don't care too much once the loop gain has dropped to 100 side. Most cases we don't really need to know exactly what's going on there anymore. And the other thing is, computers are powerful and inexpensive, and so you can just tighten reltol a little bit and make up for that factor if you want more. The third solution is to use a technique that was published by a guy with name Rosenstark, and later by Hurst, who also wrote that chapter in Graham-Meyer on return ratio analysis. So if you're really concerned, well, then here there are some alternatives. In fact, I even show you that here. In that approach, and so here, if you're already confused, don't fall asleep now, but sort of you skip the next two slides. In that approach, you need to run 3 analyses. Well, that's actually better shown here. You run 3 analyses. You first establish. You find the breakpoint of the circuit. You establish the voltage across there, or the voltage at the breakpoint. Not across. This is a short circuit. And you establish what current flows through it. And then afterwards, when you run your analysis, you actually really open the loop. But you put back the correct DC bias point from the measurement that you did here in the first simulation. So then you need to put these here and use this stimuli. Then you can really truly measure the loop gain for voltage and current, and that's numerically more stable. But again, I mean, it's not really. Okay, a much more important thing, practically, is that have you ever built a circuit that had only a single feedback loop? Did you, Gianluca? Yeah, really? Okay. Yeah. Well, now if you think about it, right, there is always a CGD, a gate to drain capacitance, right? And so basically, the minute we put the transistor there, we have 1 feedback loop. If we have 2 transistors there, we got at least 2 feedback loops. And then if we add add our own feedback, well, we have yet more feedback, right? So in practice, there is typically a lot of feedback loops, and so there were sort of challenges, right? And also the CGD feedback loop, of course, there we are totally host-with bias, because there we really cannot break that loop, right? We just cannot even break the loop. The entire loop is inside the device, so we can't get at it. Fortunately, those smaller loops very often are stable, and then we can exploit something that is not true, but in practice often true, and that is if every single block in a feedback loop is stable and the entire feedback loop is stable, well, then the whole thing is stable. Okay. So by sort of relying that every individual amplifier or every individual transistor with its built-in feedback loop is stable, or if we have multiple, if we have explicit feedback loops, so then we test every circuit that has feedback alone, then afterwards we put the whole thing together and measure also maybe the entire feedback loop. So then chances are very good that if everything was stable, then the end result was stable also. But it's not really true. We could have, in principle, circuits that are unstable, put them in a feedback loop, and the whole thing now is stable, right? And if you take a controls class, then you have examples for that case, right? That's kind of the job of a controls guy, to make stuff that is unstable, make it stable, right? So in practice, it's not so terrible, but there is in particular one case where this scheme, where we really have two feedback loops very frequently, and we need to establish the stability, and that's the fully differential amplifier, right? Circuit like this one. Probably driven by, probably there are other capacitors here, right? So here we can also exploit something. We definitely have two feedback loops, and there is no way to somehow break them in such a way that with one breakpoint, both feedback loops are broken. Hopeless, right? So, but what we can do is we can break the differential and the common mode feedback loop individually. Now, if the circuit was perfectly symmetrical, which in SPICE it actually is, in reality, not quite, right, but within 1%. Then, if we stimulate the differential feedback loop, the common mode, which is just a differential signal, right, the common mode doesn't change at all, because the gain ACDM is 0, right, for example. Likewise, if we stimulate the common mode feedback loop, the differential feedback mode isn't excited at all. So what we need is a way that we can excite just only the differential feedback loop, or just only the common mode feedback loop. And that's easy to do with our balance. So what we would do, this case, is we put a balun at the output that transforms the output into a differential and a common mode signal. Now, once we close our feedback loop, we better go back to the unipolar signals again, right? I mean the individual signals. So we go back to here we put C, or whatever we call it. And so that's the outputs of our amplifier. We put the low capacitance, all of whatnot there. So now, if we want to break the differential feedback loop, that's the point, right? And so we don't do our return ratio analysis for this point here, for this breakpoint, using the single loop method. And likewise, we can do the same thing for the common mode loop if you wish to do so. Now it also becomes clear why these baluns are so practical. If we had used some kind of a circuit that internally uses controlled sources, right, ideal sources, to generate the differential mode and common mode signal, that would have been a big disadvantage because the output impedance of that thing would have been 0 and the input impedance probably also, so the loading would not have been preserved. But if we use these transformers, then this whole thing here is really just an identity. We really haven't changed our circuit at all by introducing these two with the transformers inside. So it comes neatly together. Convenient. Okay. Okay, and so the next slide is kind of a joke. You can read it for yourselves. Apparently, there is a way to analyze precisely, and I don't know how this guy Bode figured that out. I mean, no wonder he's a genius, right? Okay, so somehow you got to go back to this Nyquist diagram, and you've learned that at some point. Trust me, we don't let anyone through this out. And that's actually useful, right? And then you, instead of tube, you have to replace this transistor, whatever you like. And by doing so, apparently you get a very complicated drawing, and in the end you can determine whether your circuit's stable or not. Okay? That's going to be the next homework. Okay, well, anyway, so. Okay, so this thing, there are now simulators that kind of help this process. This is just happening. With Spectre being the first one, where I just last year got a manual that shows that. Now, once you have done all of this, and maybe you have even gone through the complicated multi-feedback loop approach, and it took you 2 weeks, and now you're happy that your circuit has wonderful phase margin is really going to be stable. Can you be sure that the circuit is stable once you've done all of that? Well, the question is, have you still made an assumption, or have you analyzed the real circuit? Well, have you made an assumption? Yes or no? Well, what was the assumption that we made so far? We said it way in the beginning, last lecture.
The DC path is constant.
Right, exactly. We analyzed the circuit at the linearizing it about an operating point, right? And that basically tells us now that the circuit is stable about that operating point. But the circuit, we've said already, right? When we power up the supply, at least the circuit has to also go through different operating points. Likewise, during a transient, sometimes, we've seen this switching stuff where we suddenly switch a big capacitor to the input of an amplifier. Well, the diff pair is going to be way imbalanced at that point for at least some time. Right? The amplifier is going to slew and so on. Slewing in itself is a nonlinear effect. Okay, so our amplifiers or feedback loops, they're not always in that linear regime. And when they're not in the linear regime, well, then our analysis hasn't analyzed that, and consequently is not accurate. So we still need a clutch, and so once we have verified that at least if our circuit sort of is in the right place and operates the way we think it should, then it's still going to get there, right? If you're sending out a chip to the fab, I promise, you were going to run one analysis, a transient analysis, where your input is VDD. You're slowly ramping the supply up, just like it's going to happen when the chip comes back and you flip on the supply switch. If you don't do that, chances are you flip on that supply switch and the circuit never can get to the point where it's operating right. Or more likely, it will sometimes get there, but not others. And you have an unreliable circuit. Okay. So likewise, test stability by putting in big stimuli, small stimuli, square waves, sinusoids. So it's great, right? We have fast computers, so we can try lots of things. But ultimately, it's kind of these crutches that make sure that we haven't forgot anything. If you really want to be careful, then go and figure out bad things that can happen. For example, many circuits they have a startup circuit, right? We've talked about those. So they work fine if the power goes from 0 to VDD. But many of them actually fail if the power goes from 0 to VDD, back down to VDD over 2, and then back up to VDD. Right? So you got to look at such things. If you tape out a chip, then you want to know all of this. Homework for 240 is easy. Yeah. Okay, so here is a number of references. You can look at them yourselves. Actually, you see here that this stuff is actually in Gray and Meyer, so go and look at that book again. Just read the other chapter than the one that you read in class. Okay, I put in a complete example here. The example actually uses that Spectre simulator before the time when it had that feature of where it can automatically calculate the loop gain. But sort of gives you some idea of what's involved. So first of all, we have here the circuit with the feedback loop. Now here I have capacitive feedback because that's what we most of want. Now in order to bias this point here, I just use this incredibly large resistors again. Right? Otherwise, I would need all of these switches and initial conditions on capacitors and so on. That's another good approach. You use whatever you like. I just find this usually the easiest, although my amplifier now becomes, of course, AC coupled. Okay, so I also found the point where I want to break my feedback loop. That's a fine point. I could have broken it here also. Would have worked too. Right? Okay, then. Then I type in the netlist for my circuit, and Spectre has a slightly different sort of syntax than SPICE, but you probably can easily decipher what that means. And here I also refer to another sub-circuit here that I call T1, and in that sub-circuit I have put in all of that funny stuff where I test with one source and then I test with the other source, and I collect several results, right? And I use this alter statement. Again, you will this slide is here. So that sub-circuit, right? It has these two sources, and it runs a first analysis where it sets up the voltage source, and then uses the voltage source, and it sets up then a different analysis where it uses the current source. And actually first the current source and then the voltage source. Okay. And then in the end, in the post-processor, I just collect all these results. I get now this Vy, Vx, and I get the currents flowing on either side of the current source. And based on those, I type in this terrible equation that we had on an earlier slide, and I get finally my result. Plot that, and that result is shown here. So be very careful. The green line here is Ti, and it probably has a physical meaning. But the point is that it definitely looks very different from the ultimate thing, which is the blue line here. And the TV is what is here. Okay, so that's TV. And that one was Ti. And the actual loop gain that we got out of this is yet something else, right? So you cannot just look at Ti or TV. You get something wrong. And likewise the phase. Right? The actual phase looks something like this. And the phases of TV and Ti, they look totally different. Okay, so. So we can use the Bode criterion and get a lot of phase margin. After all, it's just actually why for this circuit we have a single pole here at the output. Why don't we get 90 degrees of phase margin? Well, actually, we get yeah. Why don't we get 90? We should even get maybe a little bit better than 90. There got to be another pole in town, right? Otherwise, how can you get more than 90 degrees of phase shift? Something must be there. Gene, do you think? I cannot pronounce your first name. I tried at home in front of the mirror, but actually, I thought, but either is fine. Yeah, if you have an idea, where could we get more fish? Okay. At that higher frequency port here? Yeah. Yes, I actually saw that too, and I'm not exactly sure why it is. My first thought was that it's because we have a logarithmic scale, but everything is on logarithm, right? So I don't know. I didn't make these up. I really you saw the equations. I typed those equations into the computer. So somehow I don't know mathematically how. Yeah, I don't know. Yes. I guess we could zoom in and use it on the numbers more. Now, does anybody have an idea? It's a kind of math. How can you produce this? I mean, one thing is that they may not be exactly constant. Although I would imagine that at some point when you're far enough. Maybe a numerical thing, as you know, a small change somehow that to produce this. But I'm totally on the ice. But now back to here. I actually have an idea why we get only 88 degrees of phase margin. There got to be another pole here, right? Well, I mean, the other pole's here, right? There is another node, and of course I've put some resistance here. SPICE insists on me doing that, and so I get a degree or two of phase lag. That's what it must be. Okay. So. Okay. All right. I have one more example here. That's really for this return ratio analysis. Right? Doing the same thing by hand where, again, I replace the transconductor here. I draw the small signal model. I replace the transconductor with, say, test current source. And then measure the voltage that, I need to open the loop and measure the voltage develops. So I'll let you go over this yourself. Yeah, I think we already answered it. Okay. So we are using feedback in our circuit. Once we have determined that the feedback loop is stable, we now can turn back and look at why we use the feedback, right? We want to get a certain bandwidth, we want to get a certain gain, and for that we probably use an AC analysis to determine that. Now, very often in our circuits, in our switch capacitor circuits, we actually want to know how long is it going to take for the output of the amplifier to settle within a certain value, bound of the real value. Right? And so basically what this circuit does here is that, well, depending on how we phase it, in particular if we do phase it like this, where there's phase 1, and then there is phase 2, and phase 2 here, then effectively what we are doing to our amplifier is that we are putting in a step, and the output of the amplifier is going to react something like this. Right? And we want to know how long is it going to take for the output of the amplifier to be within a certain bound. Okay? So we want to calculate the settling accuracy. Okay. So there are really two parts to the. So this is sort of what it's going to look like. This didn't come out of SPICE, so it looks a little bit. It looks like a PowerPoint. Right? But there is really going to be two things. One of them, it takes some time, and of course it could even be ringing, right? Hopefully decaying ringing of a circuit that doesn't have 90 degrees of phase margin. And then also, after we wait for an infinitely long time, then the output of the amplifier is going to settle to a value that is close to the ideal value, but not exactly the right result. And the reason we don't get to the exactly right result is that this AV0 is finite. Okay? And consequently, even after infinitely long time, there is a residual voltage. If we, let's say, have 1 volt at the output, then, and the gain was 1000, then we have to have 1 millivolt at the input of the amplifier. And that produces a static error. So when we analyze the settling time of an amplifier or such a circuit, then we generally break up the problem into different segments. And the first breakup is just we break up into static error, that is due to finite gain, and dynamic error, that is all the rest that will be a little bit more to analyze. Now, in practice, of course, all these errors, they somehow add together, and so in principle, at least, we ought to analyze everything jointly. But just like we did with noise and other or other mismatches or so, most of these errors, because they are small, right, percent or fractions of percent in a precision circuit, and consequently, linear superposition is usually not a bad thing. So typically what we're going to do is we're going to figure out what is the static error, what is the dynamic error, we add them together, and we get the total error. If we're designing a circuit, then we do similar thing. We take our error budget, we should settle the 0.01%, let's say, and we say, well, we allocate half of this error budget to the static error and the other half to the dynamic error. Or, if we have an amplifier that has incredibly high gain anyways available, and we know that we can get an almost negligible static error, then we maybe allocate 90% of the error budget to the dynamic error and only 10% to the static. Right? Okay. So now we go first and calculate this static error, and so we have this feedback circuit that we assume that somehow has been biased correctly using the switches. Right? And now we can calculate using KCL. We can write an equation here, and we know also already that the gain from here to here is AV0, right? So we have two equations, two unknowns. We can solve for V out over Vi, and that's the result. Now you've seen that. Now also, just small point here. Now you see why I'm so interested in the large signal gain. Because here what matters is the large signal gain, right? It's V out over Vi. It doesn't matter sort of where we are biasing this off, where we are biasing this away from large signal. So it's the large signal gain V out over Vi that matters, not the small signal gain. So anyways, based on this, we can rewrite this equation using a first order Taylor series approximation. We have minus C, that's the ratio of the capacitance. And they set the closed loop gain times 1 minus 1 over F times AV0. Okay? And this is now the fractional error. Okay. So in practice, then, if we want our amplifier to settle to within 0.01%, well, then this term here better be equal or smaller than 0.01% or 10 to the minus 4. The example is on the next slide here. Suppose that we need a closed loop gain of minus 4. That's given by our application. Let's assume that we have certain values of capacitors here. CF and CS, they are ratioed in 1 to 4, so we get the closed loop gain of 4, that's correct. But we also have the CP that sets now our feedback factor F. And if we want, in this example, it's just 0.1%. So then F times 1 over F times A should be smaller than 0.1% or 0.001. 0.001. So in other words, F times AV0 should be bigger than 1,000. Now, because F is 1/6, that means that AV0 must be at least 6,000. Very common mistake, right? I have an amplifier and I want to have a settling accuracy, a static error that is no bigger than 0.1%. That corresponds to a gain of 1,000, but it's the loop gain that needs to be 1,000. If I have a feedback factor that's less than 1, like 1/6, then I actually need a bigger gain. Right? Very common mistake. Okay, so again, of course, if the overall error specification is 0.2%, well, then that would leave another 0.1% to the dynamic error. If the overall error specification is really 0.1%, I probably would need twice this gain or so to leave some of the error budget for the dynamic error. Okay. Don't fool yourself when you start designing. If you give all the error to one thing afterwards, you're going to have a hell of a time meeting the other requirements. Okay, so this was pretty simple, right? Now the dynamic errors. There is a lot more to those, and they are a lot harder to analyze, and we are going to need a lot more crutches and helps and so on. So I again put the slide here that sort of tells all that we are going to do, but yeah, it will. Sometimes we might lose almost sight of that we are really talking about settling. So finite bandwidth of an operation amplifier, of course, comes into play. The feed-forward zeros, the thing that we talked about, right? That heck, I mean, the feedback network also starts contributing a signal at the output. Well, that also can affect settling. Non-dominant poles, right? The thing is not going to have a 90 degrees of phase margin, and so we may see some ringing. Doublets, we talked about those a few weeks ago, right? We talked about those small artifacts in the frequency response that we get, for example, if we use a gain booster. Right? And they, it turns out, affect settling time. And then there are nonlinear effects, in particular slewing that you probably already talked about. They also affect the settling time. So analyzing the dynamic errors, really, there's a whole slew of things. And now we could write equations, complete nonlinear differential equations, sets of differential equations, and we couldn't solve them, right? And so we are going to go again do the same old thing. We are going to go and analyze one of these errors at a time, and then we sort of put these results together and pray that the superposition sort of works. We can handle that. All right, so first approach, again, simple. That's kind of EE40, right? A single time constant, linear circuit. So here, all I've done here is I replaced, instead of having here an amplifier with a fixed gain, which is a reasonable model if I'm willing to wait for long enough, I replaced this with a transconductor. Combined with the low capacitance, the feedback loading, and so on, that gives me a finite bandwidth. It's one single time constant in this circuit. At this node here, because the only capacitor is just a divider, right? So now again, now we are sort of, you can now use your favorite technique to analyze this circuit. You can use 2 ports, and don't forget about the feed-forward here, or you can use return ratio analysis, or you can, and that's what I've done here, you just can use plain old KCL. And you also get 2 equations, you can solve them, and I got here the closed loop gain. Notice again, I mean, the phase margin of this or something like that is totally immaterial for stability. If I wanted to put another feedback loop around all of this, then I would be concerned with the phase margin of this. But for stability, really, I would have to check into this feedback loop alone. We've done that in the earlier part of this lecture, right? So now we've done that. We've assured that the circuit's stable. Now we want to know what is the closed loop response, so that ultimately I can figure out what is the step response. I put the step in here. What comes out over there, right? Okay. So for that, from my equations, I solve first the frequency response, and here again, I mean, it's very, very helpful to bring the result into some reasonable kind of a configuration. I factored out here the gain, right? Ideal. And that is dead on, this ideal gain. Why? Well, because here I implicitly assumed that we have infinite gain, because I left all the RLs and ROs and whatnot out of the picture. Again, the same argument as we had used earlier, that when things go fast, well, the bulk of my current goes through the capacitors anyways, and the little trickle current that also flows through these current source output resistors is sort of negligible, right? And so I simplify my equations, of course, greatly by not having them there. But the trouble is that now it looks as if I got the perfect DC gain. But we've said that already. We analyzed that separately and just add the result then to get the overall settling accuracy. Okay, so we get a 0. So if you had done 2-port analysis, would you have gotten that 0? Right. So this would be missing, and we'll just see that that's not necessarily always such a good idea. Or you would have to augment the 2-port analysis. It's possible to include also the feed-forward current. And then here, this thing we have seen already before. That's this CL star or so, right? We don't see only the load capacitor here, but we also see a fraction of the feedback network. Okay? Specifically of this feedback capacitor, and the fraction that we see is is determined by the Miller gain around this capacitor CF. And this Miller gain is 1 minus the feedback factor. So it makes perfect sense. And then here we have the transconductors. Okay, so now we have to gear up to a little bit of math, but let's look at this. So we have a pole and a 0. The pole that really sets the bandwidth of the circuit, and it tells us how things are going to happen over the long run. The 0 tells us what's going to happen to the immediate response. In particular, we remember that we have all these capacitive feedback networks that goes all the way from the input of our circuit through a bunch of other capacitors, ties all the way to the output. that even if the amplifier wasn't here, if we hit this with a step, we get a step out here. So we get an initial response here that incidentally always goes in the wrong direction. And the first thing that our amplifier is going to do is it just undoes the initial damage that was done through this feed-forward thing. Right? Because the amplifier is finite bandwidth, but the feedback network, if there are no capacitors, if there are no resistors here, it's actually infinite bandwidth. So the feed-forward network is faster. Okay. So now the way we analyze this is, of course, inverse Laplace transform. So we have to put a step in. A step Laplace transform is a step is 1 over s. So we have to take our frequency response, multiply with 1 over s, and then do the inverse Laplace transform. And if you can use more zoom, just about this here, a little more zoom. Well, okay. Hopefully you can read it in your notes. Okay. But then, is it on focusing on your side? Right. So again, I formulated the result in a convenient form. This is really the ideal response, right? If our amplifier was perfect, then the output would be just the ideal, the step, the input put in, inverted, and multiplied by the gain we set with the feedback network. Okay? And then all of this additional thing here, there is an error term, right? And we see here, and we probably remember that also, that the error is decaying exponentially, and the time constant determines how fast the error is decaying is set entirely by the pole, never by the zero. It's good to remember. Okay, and the amplitude of this error, well, that depends on the pole and the zero and so on. If we didn't have the zero here, then this would be just 1. If we have the zero also, then the amplitude actually is going to be larger than 1. Okay. Actually, there is there's something neat. I put a little note here. There's something neat about this circuit. This thing we want 0, right? How can we do that? How can we make this 0? Hey, I mean, come on. This is now really trivial. This is high school. Well, I'm going to ask my second grader at home. He's going to tell me. Yeah.
Make the pole and the zero the same frequency?
Yeah, exactly. I mean, there are two possibilities, right? What we normally do is we wait for an infinite amount of time, right? And then this term is going to be, yeah, the pole is negative, so this term is going to be 0, right? P is negative. Or, much more clever, P equals C. And this term is 0. You can build an infinitely fast step amplifier, pulse amplifier. Have you ever, do you think there's of any use? Have you ever used a circuit that does this? Have you ever used an oscilloscope? Yeah. Well, you've used such a circuit. Have you ever gone through? The first thing you do with the oscilloscope in your first course on a lab on oscilloscope is you have to put in a square wave, right? And then there is somewhere a screw somewhere on the oscilloscope or on the probe. And you turn that, and the square wave is going to look. Yeah, the ideal square wave is going to look like this. But when you first turn it in, it's going to look like this. Or maybe it's going to look like this, right? And as you turn, it's going to look one or the other, right? Right? And as you turn the screw, you can get from this situation to that situation. In the middle somewhere, you get this situation, right? That's when P equals C. Bingo. That's what you do in an oscilloscope. Everything has a use in analog circuits, right? So that 0 is not such a bad thing. Now, why don't we do this? I mean, it sure beats on an oscilloscope. I mean, how would we actually do that? The fastest oscilloscopes, they have something like 20 gigahertz or even more than 20 gigahertz bandwidth. I mean, how are you going to build an amplifier that you have like 10 time constants or 8 time constants to weight, right? You need an amplifier that the bandwidth of almost a terahertz. Nobody can do that, right? Need that. So you need to solve the problem like this, but why are we still most of the time we are actually going for the alternative? We're going to wait forever. Why don't we always just we use our op amp and we put a little capacitor around it in the feedback path, right? We make an infinitely fast amplifier. Why don't we always do that? I can think of at least 2 reasons. One of them is, how precisely can you match P and C? Percent, right? Well, if you look at it on the screen of your oscilloscope, probably the matching is not 1%, it's probably something like 5%, because the screen is small and your eyes are, and the beam is wide, right? So it's not very accurate. But you don't need it more accurate than a few percent, right? Which is fine. So accuracy is the #1 reason. Right? On the other hand, in operation, in an A to D converter also, you want this error to be 10 to the -5 or something like that. And then really you never can get this matched. Right? And the other thing is, of course, you're really relying, at this point, you're really relying on the input driving the output, right? And so the impedance of this circuit may not be just quite ideal, right? You may want to have a more constant impedance over a broad range of frequencies. I mean, that's another thing about an oscilloscope probe, right? They tell you that, oh, the input impedance of the oscilloscope is a megaohm or something, or 10 megaohms. Well, yeah, sufficiently low frequency, right? And the higher frequency, of course, not. Okay. So everything has a use. So let's try to so the time we can now compare back to what we had before. The time constant here is simply the effective capacitance divided by the GM and 1 over 8, and multiplied with 1 over 8. Okay, so that's the time constant. So if we then later want to have an amplifier that goes at a certain speed, that settles to a certain accuracy, this tells us we have to figure out CL effective, we have to figure out CF, and based on that we can figure out GM. Then we can design the amplifier. And of course here we also see that heck, this F term we really would like to be as big as possible, right? F is always less than unity. And then the ratio of the pole to the zero frequencies is given here. So I guess we want this small, then actually large LF would help. Okay. Now let's draw our conclusions for 2 different cases. The first case, let's assume that this ratio of P over C is actually much less than unity. Let's look at what actually it is. So yeah, it's first of all the feedback factor F. Well, if we want to realize large gain, right? 1 over F. Well, the feedback factor is always smaller than 1 over C, 1 over the closed loop gain. So if we want to have a huge gain, C, then that means that F is going to be very small, even smaller than 1 over C. Right? If we want a gain of 4, then we are going to have F being less than 0.25, probably a bit less. We have 1/6 in example. And the other thing is that this ratio, well, often the low capacitor, of course, is larger than the feedback capacitor, and so that is not unrealistic. I think the case where this P over C is much less than unity will really happen whenever we want to get a reasonably high closed loop gain. Right? So in that case, our our equation now simplifies to simply the first order response, the decaying exponential. And if you can use again more zoom, sort of my half slide. Thank you. And so now what we usually care about is the relative settling error. We don't care about the settling error in microvolts or something like that. Most of the time we want to have the relative error not to be bigger than something, right? So we can calculate that. So the relative error is simply the ideal output, which because we neglected the load resistance, is simply the output that we would be getting after waiting for infinitely long, minus the actual output. Well, that's the output taken after not waiting infinitely long, but waiting for TS, where TS is the settling time, right? The allocated settling time. If you have an A to D converter, goes at 100 megasamples per second, then a period is going to be 10 nanoseconds long. Most of the time, our amplifier has only half a period to settle, so in 5 nanoseconds it will have. So then this TS would be 5 nanoseconds, and we divide again by the ideal value, and then this just comes to this error here. So that's the relative error. So now I can invert epsilon. The relative error is equal to e to the minus t over tau. I can solve like this, and I can find out what is the ratio between the settling time and tau as a function of the accuracy that I'm demanding in my application. So if, for example, I set epsilon to 0.01, that means 1% accuracy. So that would be good enough for a scope, probably, for a scope screen, right? And then I need to wait for 4.6 time constant. In other words, if my amplifier's time constant, right, we had that on the slide before, this time constant here is 1 nanosecond, and then I would have to wait 4.6 nanoseconds so that my error has to decay to no more than 1% of the exact result. Now again, I mean, be very careful. We are dealing with a very large number of errors here, and right, slewing and all of that stuff. Right now, we are analyzing only linear settling for a single pole, no zero. Right? In that case, that's correct. If we wanted to have 0.1% error, then we need to wait about 7 time constants. And so, and if we wanted to have an error of no more than 1 in 100,000, so that corresponds to about 16 bits, right? 16 bits is 1 in 65,000. Then we have to wait for 11 some time constant. Thank God for the logarithm here. That means that even if we want blazingly high accuracy, we don't need to wait forever, right? I mean, 1% isn't very good accuracy, but we don't need to wait sort of 10,000 times longer to get accuracy of 1 ppm. We need to wait only, 3 times longer, and then we get to accuracy 1 ppm. Right? Thankfully for this logarithm. Otherwise, we probably could. Yeah. Otherwise, if there wasn't this logarithm here, we couldn't build very fast analog circuits at all. The exponentials decay exponentially. Right? Okay, so an example here. So we design, again, this thing with a closed loop gain of 4 or minus 4. Again, chosen some capacitors that give us this. Now my settling time that I allocate is 10 nanoseconds again. Some A to D or whatever application sets that. Accuracy 0.1%. I calculate the feedback factor. I calculate L effective, which is a little bit more than CL. CL was 5 picofarads. I verify that P over C is much less than unity, because otherwise I can't use the equations that we just looked at. And then I can find the tau for my amplifier, 1.5 nanoseconds. Right. Oh, no, now what? Now I based on 0.1% accuracy, I need to use this line here. So I need 6.9 time constant settle. Well, I have a total of 10 nanoseconds, and so that divided by 6.9 is the time constant that my amplifier must have in order to have available a full 6.9 time constant settle. And based on that now I can figure out what is my transconductance. Apparently I need 24 millisiemens. That's what I designed for. And we know how to do that. Okay. So here is the other case when P over C is not negligible, right? So that really happens when I want to have a closed loop gain that is not very large. In particular, when the closed loop gain is, like in the example here, is actually quite a bit less than unity. Does it make any sense? Am I now grinding through this only to really and definitely put everybody asleep? Or is there merits to that? Well, it's not so obvious to see. For building an amplifier that attenuates the input signal by a factor of 4, right? That's what this means. It's probably not very, very interesting. Right? I'm not sure, but these switch capacitor circuits we're going to see later, they also can be used for signal processing, in particular filtering. Switch capacitor filters, and there are plenty of cases where how do we build a filter? Well, we pump our signal through all sorts of switch capacitor stages, one after the other. And every switch capacitor stage has some gain, at least in the passband, right? The signal gets bigger and bigger and bigger, and after a while it just gets too big. Moreover, if we have some peaking or ringing or so, we really need to attenuate the signal so that at the intermediate nodes it doesn't exceed bounds. A very common application of where we need gains of less than unity all over is in sigma delta A to D converter. There we have a chain of integrators, and invariably the signal keeps growing, and big problem, right? So usually these integrators, they have a gain there, like a fourth, a fifth or so, right? So that really happens. And in fact, once I had a student who designed the sigma delta ADC, and he started out with designing a perfect amplifier, everything and so on, based on this assumption. And then when he looked finally at the sigma delta, he said, well, gee, I need to actually attenuate my signal, otherwise I could go out of supply rail, right? And then he was in this case, and the amplifier design, beautiful amplifier, was totally useless because this equation then said, well, yeah, you meet this spec, but you don't meet this spec, right? And this is what he wanted. Okay, so in that case, now we need the full equation, and now the relative error is this thing, and we can again solve for Ts over tau, and that's now a more complicated thing, not just the logarithm of epsilon, but the logarithm of epsilon star, where epsilon star is epsilon divided by this thing, and this thing presumably is less than unity, and so we need more. Okay, so again we can go through this equation and figure out what the feedback. Now, one thing that is very nice about this case is that when we generate attenuation with such circuit, generally the feedback factor can get very, very large, very close to unity, and that's what we have here. 2/3, the effective low capacitance, and then that's just this here, Ts over tau. So now I need 7.3 time constants to settle, and based on that, again, I can figure out what is GM. Okay. So actually, P over C is a half, right? So we really would have made a 50% error on our settling time had we ignored P over C. Not so good. Okay. See you next time.